The James Webb Space Telescope, JWST, humankind's most recent inestimable eye, connects across incomprehensible distances, catching light that has traveled for north of 13 billion years. This light, anyway, lets us know something other than a story of time. It uncovers the advancement of our universe, shaped and extended by its continuous expansion. As we peer back at the most far-off systems, we're basically seeing an old period moving increasingly close to the commencement of the universe, the Big Bang. The theory of prehistoric cosmic detonation, a primary story of modern cosmology, strongly proposes that our universe had a particular start and is limited in age. Yet, from its initiation, this solitary inestimable beginning has been met with incredulity, and difficulties to its legitimacy continue even in standard cosmology for quite a long time. The theory of the universe's origin held solid, particularly after the discovery of the infinite microwave background, CMB, during the 1960s. This foundation radiation, a weak, comprehensive murmur across the universe, adjusted flawlessly with forecasts of a hot, thick early universe. Anyway, weighty observations by the JWST lately feel a little wary and have brought up new issues about the Big Bang's authenticity. Through the astounding lucidity of the JWST, NASA's enormous time machine, we've seen bunches of antiquated systems far bigger and more various than anticipated, testing our comprehension of the universe's earliest stages. As the telescope peers back to when the first systems formed, it offers humankind a remarkable view, one that the Hubble telescope could not completely access. Hubble was essentially not adequately sensitive to distinguish the incredibly faint redshifted light of these earliest systems. However, with JWST's best-in-class capacities, we're looking as far as possible back, really close to time itself. As we venture into this unknown domain, we encounter an age-old mystery. How did the first worlds truly structure, and does the universe, as far as we might be concerned, truly have a single conclusive start? The earliest universe was a hot, dark spot so thick that light itself couldn't unreservedly travel. This implies that, regardless of how strong our telescopes, we can't notice any further back with light. Anyway, we are not restricted to light alone. New mechanical headways are making the way for the recognition of gravitational waves from impacting black holes, which could act as a new road to peer once again into the universe's early stages, maybe even into the very peculiarity we call the Big Bang, the foundations of the theory of how things came to be. The theory of the universe's origin and its developing wariness stretch back to the 1920s and 30s, when stargazers first noticed that far-off systems appeared to be getting away from us. This discovery, combined with Albert Einstein's theory of general relativity, set up for the Big Bang model. Einstein's conditions anticipated that a static universe would be unstable, requiring either constriction or, on the other hand, expansion. Seeing this development suggested that systems had probably been closer together in the far-off past, suggesting a touchy start for the universe. The universe's extension has a few significant ramifications. Not only do objects move farther apart, but the light discharged from them extends, moving to longer frequencies as time happens. Since frequency corresponds to energy, with more limited frequencies being more fiery, this redshift means the universe has been cooling as it ages. By rewinding this enormous expansion, we arrive where everything would have been so hot and thick that neutral molecules couldn't exist, prompting a uniform, singing, hot shine. This glow was confirmed in 1964 when stargazers Arno Penzias and Robert Wilson coincidentally found the vast microwave background, an inescapable radiation field faintly repeating the universe's blazing beginning. Yet, as the JWST pushes the limits of vast perception, researchers are finding features in the early universe that strain the conventional Big Bang story. We see huge, radiant cosmic systems where there should be none, grouping in manners that challenge assumptions. So, if the theory of the universe's origin alone doesn't make sense of these irregularities, what else could? At the core of the Big Bang hypothesis lies a peculiarity, a point of boundless thickness and temperature where the laws of physics break down. This is where existence, time, and space, as we know it, began. However, this idea, while strong, has limitations. Envision trying to describe the sum of existence packing into a limitlessly thick point. This is where our comprehension reaches a stopping point. Despite the fact that numerous parts of the Big Bang model have been upheld by observations and lab tests, this initial peculiarity remains a riddle. making one wonder, might the universe have had an alternate kind of starting? In its journey to understand the universe, science has found ways to reproduce similar circumstances. For example, quark-gluon plasma has been combined in laboratories, and matter-antimatter matches have been created to line up with early universe expectations. Through these analyses and by dissecting the infinite microwave background's variances, we have a well-supported image of the universe's advancement. Yet huge secrets remain. For instance, if all regions of space were once compacted into a solitary point, why do we notice such uniformity in the universe's temperature? By conventional models, areas of space ought to show fluctuated temperatures since they could not have had the opportunity to trade energy or information. Also, we could hope to track down leftovers from the hottest events, such as magnetic monopoles or spatial anomalies, but none are observed. These errors open the door to further possibilities. Either the universe intrinsically had these adjusted properties all along, or there was some component that forced these circumstances. One candidate explanation is vast inflation, a fast expansion conjectured to have happened prior to the Big Bang itself. On December 7, 1979, physicist Alan Guth proposed this revolutionary thought. He guessed that, prior to the hot Big Bang, the universe experienced a remarkable expansion. This inflationary stage could make sense of why the universe appears flat, homogeneous, and isotropic. After inflation, the universe would change into the hot, dense state associated with the Big Bang, making way for galaxies, stars, and planets to form. Anyway, as researchers now acknowledge, even infinite inflation does not resolve every peculiarity. For instance, historic observations by the JWST have uncovered shockingly large galaxies from the universe's early stages, suggesting a sped-up formation rate that inflation alone doesn't explain. The JWST's incredible capacities offer humankind an exceptional look into the universe. This $10 billion infrared telescope has captured stunning pictures of the early universe, revealing a variety of huge, brilliant worlds from when the universe was just a fraction of its ongoing age. While astronomers previously believed they had a strong understanding of how matter coalesced to form the first stars and galaxies, the JWST discoveries suggest a considerably more rapid development than anticipated. These observations have stirred both excitement and skepticism among researchers, as some scholars are compelled to return to key assumptions about universe formation. According to astrophysicist Erica Nelson, enormous galaxies seen within the first 500 million years of cosmic history defy existing models. The JWST's preliminary findings indicate that galaxies in this early epoch may be far more massive and varied than previously thought, possibly housing masses equivalent to today's large galaxies like the Milky Way. This rapid development challenges current cosmological models, which suggested that a galaxy of such scale wouldn't form until 1 to 2 billion years after the Big Bang. Nelson's research proposes that galaxies may develop more forcefully than expected, prompting the possibility of new theoretical structures for cosmic evolution. Dark matter, an imperceptible and mysterious substance, is believed to make up about 85% of the universe's mass, shaping the large-scale structure of the universe. Traditional cosmology proposes that galaxies form inside massive halos of dark matter, which gravitationally attract normal matter, allowing stars and galaxies to coalesce. Yet, JWST observations challenge this model, as galaxies appear to be forming in ways that challenge our understanding of dark matter distribution. The existence of dark energy, a similarly elusive force responsible for the universe's accelerated expansion, further complicates the picture. Some models propose that early dark energy, a brief lift in dark energy density, might have accelerated galaxy formation, possibly aligning with JWST discoveries. Anyway, such changes must fit within the broader framework of the standard cosmological model, which has already explained cosmic expansion on large scales. As convincing as the Big Bang hypothesis is, it is not the only explanation for the universe's origins. Several alternative theories have gained attention, each offering intriguing perspectives. The steady-state theory, unlike the Big Bang, proposes a universe without a beginning, where matter continuously appears as the universe expands. This theory suggests that, as galaxies move apart, new matter is produced, preserving a uniform density. However, it fails to account for the CMB, which strongly supports a hot, dense early universe. The mirror universe hypothesis, a more speculative idea, suggests that two universes were born in the Big Bang, one moving forward in time and the other backward. This twin universe would develop backward, providing a mirror image of our own cosmic history. Though highly speculative, it proposes that the universe could be more complex than previously imagined. The simulation hypothesis raises the possibility that our universe is a simulation created by an advanced human civilization. Quantum entanglement and the unique nature of spacetime lend a theoretical weight to this idea. Despite remaining unprovable, the simulation hypothesis poses questions of fate and reality, testing how we understand existence. The multiverse hypothesis, a popular alternative, proposes a limitless number of universes, each with its own physical laws. According to this model, dark energy fluctuations trigger numerous Big Bang-like events, creating a vast multiverse. As our universe expands, creating a void of dark energy, this model suggests a continuous cycle of creation, destruction, and rebirth. Each of these hypotheses offers unique insights into cosmic origins, raising new questions about the nature of space, time, and matter. While the theory of prehistoric cosmic detonation remains the prevailing explanation, it has been tested and reshaped by new evidence and new perspectives. The JWST, with its unrivaled sensitivity, is poised to unlock even more secrets of the universe. As the telescope continues its mission, forthcoming spectroscopic data will enable more accurate measurements of distant galaxies, allowing scientists to refine their understanding of cosmic evolution. As the James Webb Space Telescope, JWST, continues to expand our journey into the universe, its discoveries promise to reshape how we understand numerous fundamental cosmic processes. One area likely to see significant updates is the formation and evolution of galaxies. Generally, researchers believe that galaxies formed from small clusters of matter that grew over time, organized by gravity. However, the JWST has uncovered evidence of galaxies that appear to have formed much earlier than previously thought. These early galaxies are not just bigger and more varied than anticipated, but they also seem to have developed complex structures in a fraction of the time scholars had envisioned possible. This raises fascinating questions about the processes driving galaxy formation. While gravity certainly plays a crucial role, the discovery of such large galaxies in the early universe suggests that other factors may be at work. One hypothesis involves the role of supermassive black holes, which could serve as a central mechanism for galaxy formation. If these black holes formed early in the universe's history, their powerful gravitational pull could have accelerated the rate at which surrounding matter clumped together, leading to the rapid formation of large galaxies. Additionally, the energy released by these black holes could have triggered bursts of star formation, further speeding up galaxy development. The JWST's ability to detect light from the earliest galaxies also offers new insights into the chemical composition of the universe at different stages of its evolution. Earlier telescopes, like Hubble, could observe distant galaxies, but their sensitivity was limited when it came to detecting the faint light emitted by early galaxies. JWST, with its larger mirror and infrared capabilities, can observe galaxies that existed within the first few 100 million years after the Big Bang. These observations are revealing a universe that was much more chemically diverse than previously thought. For example, the JWST has identified galaxies that appear to contain metals, elements heavier than hydrogen and helium, much sooner than cosmologists had anticipated. This suggests that star formation in the early universe may have been more complex, with the first stars enriching the surrounding gas with heavier elements much faster than expected.